have that I got paid for grad school or whatever with it. Yeah, it's like they won't come to time and all like but I take another grad school and like he likes that. You decided to go there. Yeah, you could try. Like the way that you read esoteric things.
Both the define like get into it, but yeah, then there's nothing. Don't worry about it. I think it is. Should draw.
Okay, guys, let's start. Let's finish. It is the finish. I mean, a couple of things, right? So first of all, I ran out of time, which is not ideal. Second of all, I almost finished, which is almost good. The biggest flaw, I mean, the biggest bug or whatever, which we had is that I did not assign the homeworks, right? So there is essentially this class is incomplete without 2 or 3 more homeworks. One is ELF / first process. Another one is context switch. Plus scheduler. And from the last 2 lectures, we know that no one knows how to build the proper scheduler. So something like round robin or simple O1, which we discussed, will work for now for this microcontroller. And then third homework is IPC, interprocess communication. And I mean, it's unfair to just leave it like this. So I will actually assign those homeworks at their option. But otherwise, I mean, I still, like, there are some people who are still struggling with homework 3. So I'll push those, like, hopefully this one tomorrow. And these 2 maybe later this week or next week. And they're completely optional, right? So you don't have to do them, but I encourage you to do them. And next year, I will make sure that we'll at least get to this point. So essentially, like, I'll streamline everything, make sure that these two homeworks will be assigned. But right now, not. Well, you don't have to. Like, if you're worried about your grade, and I'm pretty sure that I hope that no one is worried, then try working on this one and talk to me and submit it. We'll figure out a deadline just to make sure that you're happy with your grade. But essentially, in order, like, okay, we talked about how to build things, but unless you build those, it's kind of like, I don't think that your knowledge is complete. But I'll make write-ups for these 3, and then I encourage you to go and take a look at them and at least, like, imagine how you build them, right? Okay, any questions?
What is the deadline for these things? Because I'm still trading on one.
Oh, we'll figure it out. Like, just ping me.
Okay.
I mean, like, there is a physical deadline to give you grades,
Yeah.
which university forces them.
That's the one that I'm trying to. I don't want to take more time.
Yeah. So talk to me and we'll figure out. But I know that you might have other midterms and stuff, so I don't want to push you. Okay, cool. Then yeah. So let's discuss. Send me an email. So, like, I can give you enough time to make sure that you finish a couple. And there will not be, if you follow the lectures, they shouldn't be that hard, but they are, like, so you have to work on them. And okay, so and this is fine. So, but still our story, it's almost complete in a way that, I mean, if you listen carefully to what I was saying, you kind of know how to build this microkernel. We said there is this one little thing which we don't know how to build, or we never discussed. So who can guess what is this one little thing? Like, just to make sure that we understand where we are. we know how to build the microkernel, not just at least hypothetically, and you build parts of it. It has a memory allocator. It has a notion of creating the first process, right? So it has a notion of thread of execution. We talked about context switch, so which means that if you do a syscall, you create more of these boxes, which are processes in our microkernel. This is like process 2. We can come up with some bootstrapping protocol where this guy, for example, have ELF images for other processes, and this gets loaded into this. We know how to build a context switch, meaning that those threads of execution are running like if you're running on the same CPU, you keep context switching, so everything is running. You come up with new additional system calls which allow you to create multiple threads of execution in the same process, right? So this is like T3, and we have some kind of a scheduling queue, right? And you just essentially pick the next process to run. You keep context switching. We didn't get to discuss to the point when we were discussing device drivers, but essentially we talked a little bit about it. But the idea is that one of those boxes will be running something like network interface, like device driver, and the way it works is that you just roughly speaking map the bar region of the device into the address space of this process. This way, the device driver communicates with hardware, creates submission and completion queues to communicate with the device. What we haven't discussed that we actually need to set up something what is called the IMMU here. It's like a page table which sits between the device virtual memory and the physical memory of the machine, right? And to make sure that device can only override, for example, the pages and can access this page, which are like essentially to prevent the device from overriding the memory of the machine, right? So because otherwise it can just not writing anywhere in kernel memory. And it used to be like this before IMMU, but now device sits behind IMMU and can essentially, you will implement a system call, which says, okay, here's the page with the virtual address A, please, like an easiest mapping is like saying 1-to-1, for example. You say, please map this virtual device address, which matches this VA into the physical address, which backs this page. So roughly speaking, if this page sits somewhere in physical memory, there is an IMMU is a page table, which is almost identical to a normal page table. And you say, look, this virtual address is mapped specifically to this page. And then both this process and the device can use this virtual address to access this physical page. And so essentially you map those queues. Inside the queues, you place the virtual address to specific packet payload, for example. You write into the bar region saying, okay, there's something in this queue. And then device essentially picks it up, like it sees the bar region as some other virtual address. So if this is the page which maps the bar region, the device reads something from the bar region, picks up something from the queues, and send the packets on the wire, right? The story is, I mean, I know that I go very high level, but it makes sense, right? So this is how you communicate with devices, right? And so essentially, fine. So you almost like, what I'm arguing is that you almost can build a POSIX-like environment in which, you know, maybe you have your own TCP/IP stack running as a library in this process. You use inter-process communication, and we discussed IPC to talk to the device driver. Maybe you have multiple processes, right? And multiple IP stacks, but essentially device driver implements some kind of a multiplexing. Like, and as we discussed, it makes sense to probably establish this shared ring buffer style asynchronous communication for fast communication with device drivers. But essentially you get like, instead of doing system calls like in Linux, you just send messages across to the network interface and it communicates with IO, and that's essentially your system, right? So we kind of like running it. We can discuss how we can build something like a shell for this system. It's a cute exercise, but let's just for a second stop here. So this is a typical microkernel, and you kind of have all the knowledge for how to build it. As I was saying, you have memory manager, you have you know how to build scheduler, you know how to build system calls, you know how to start the first process, you know how to build IPC inter-process communication mechanisms, you know how to implement the system calls which allow you to create the second process, create additional threads of execution, and essentially we didn't talk much about IMMU, but it's not that hard. But essentially, as long as you allow a specific process to map bar regions of the device or a specific device, and the way to do it is that you will run something like your boot manager, for example, will enumerate all PCI devices, identifies all these bar regions, and for example, it has enough knowledge that, okay, like a bar region, it finds a device with a specific ID, looks at it, says, okay, look, I have an L file which says that it will handle this device. It's kind of like a load, like extended, it's like a Linux kernel model which says, okay, I will handle this specific flavor of a device. You can then create a specific network device process or network device driver process, and then said, okay, look, here's the bar region, so start handling this device, and please advertise a communication point, and I will later, whoever wants to connect to a network device, I will pass this communication point inside, and this is how these connections will be established, for example, right? And there are different ways to do it. So for example, you can do something like this guy, and it's a little more sane. Instead of like bundling everything together here, say, look, this guy is very dumb, but really it just creates another process which handles the PCI bus and essentially just something like maps all the bar, like essentially allows this guy to enumerate the PCI bus, find all the bar regions, and then this guy will either this or another manager will be managed, like will create enough, like if you have infrastructure to say, look, this specific ELF binary is actually a device driver, and you can imagine how you can implement it, like saying that like some metadata which says, okay, this ELF handles this specific PCI ID or device ID, then just to start a new process and like play a communication protocol between a new device driver, saying, okay, like I know that you're ready to handle certain PCI or device ID. Take a look at this bar region. Are you okay handling this bar region? And if this piece of software says, yes, I'm pretty sure I was designed to communicate to this device, and you kind of, this becomes your network interface, for example. And then you kind of like go through all of them. And this is what Linux does, essentially. Linux does the same, but inside the kernel. So what it does is that all the loadable kernel modules, I mean, I think Linux, I mean, there's also a protocol and how they, but at some point, like they all register with the kernel, and then the kernel itself goes and enumerates PCI bus and essentially says, okay, do I have anyone registered for this PCI ID? Sure, like, and then they play like a probe protocol saying, okay, yeah, I will be handling this device. And sometimes you cannot find it, and then this, like, there is no device driver in your system, right? Because you didn't have this flow. But essentially, it's more of a software engineering, and it's not like super hard to create different constructions for how you essentially implement this idea that you have like kernel extensions, which can handle specific device drivers. And in our system, they will be running as different processes, right? And okay, sure. So if you say, look, but guys, that's all fine. And we can build it, and like someone like Google, for example, hires you, says, okay, we want to run it on some embedded device, like a camera or something. And you say, yeah, I clearly understand this picture. We did it, we can build it. And all the microkernels will kind of have this flavor. And then your user land, then this kind of part, roughly speaking, because it becomes your operating system, although it runs. There is a tiny part which runs in ring 0. Everything else runs in ring 3. But really, it forms your operating system, and then applications run on top. And we just essentially use high-level interfaces. Sometimes they can talk to the device driver directly, but sometimes they will go through some process which maybe implements something like TCP/IP stack for them or something like that, right? And then the connection goes through this TCP/IP. So, and that's pretty real. So this is how those things are deployed today on different like embedded platforms, maybe even mission critical platforms like drones or autonomous systems. The advantage of this architecture is what? Let me ask you, compared to monolithic kernel.
Your drivers aren't in the kernel and they're unprivileged.
Yeah, so what does it give us?
Well, the Linux kernel is mostly drivers, and that's the most buggy.
Yeah, so Linux kernel is 70% drivers. And like people do disagree on, like 20 years ago, one person made a claim that device drivers have a higher density of bugs per line of code. And 10 years later, another person said, okay, guys, we worked for 10 years, we're so good that now the density is almost as the same as the rest of the kernel. And so this is where we are. We don't really know really, but like this argument is it's probably a slightly higher density. Why? Because those device drivers are implemented by third-party people who often have incomplete knowledge of the kernel, and no one has a good complete knowledge of the kernel. But like people like you graduate and say, look, I will be working for Intel and will be writing device drivers for their next whatever network interface, right? And it may happen that you have a bug. And so yeah, so Pali is right. So we have a higher density of bugs, but also just taking into account this size, and with every generation of hardware, we need new device drivers, then the bugs are probably frequent, which means that in this architecture, if you have a bug, first of all, you have a bug in ring 3, you cannot really attack the microkernel trivially because your system call interface is reasonably narrow and and maybe you even have a verification argument about your microkernel. So essentially, you most likely can cause a denial of service because there is no real easy way. You will see a lot of arguments that you can micro reboot this subsystem. I mean, like people make careers on this, saying that in a microkernel, it's possible to reboot a crashing subsystem and everything will go fine. That doesn't always work because there might be a dependency between the network stack and a network interface. And then the network stack says, okay, look, guys, everything was connected, set up, and suddenly you say you rebooted, and what do I have to do? Reset everything again. So there is some kind of a non-trivial catch-up between these two. And especially in the case of a network, it's probably feasible because you say, look, wow, yeah, network packets can be lost anyway. But if you have some SSH keys which suddenly disappear from this domain, you have to reload them from somewhere. So I kind of argue that micro reboot is not really as practical as advertised, but maybe feasible in the future. But really, what happens is that you reduce vulnerability or lower vulnerability from potentially full control over the system if you discover it ring 0 in the kernel, like in the Linux kernel, to a denial of service where the system has to reboot. I mean, which is not ideal if you're flying a drone, then it crashes and maybe you lost it, but still better. But that's one argument, which I agree with it. So what's the other advantage of this microkernel architecture? well, yeah, go ahead.
Maybe you would say it's small enough to verify.
Small enough to verify. I agree with this. And like Linux is 27 million lines of code. So like by switching to microkernel, like complexity will only go a little, will become a little higher because, right, you cannot, semantically, it's all the same. You're running these things, but now you also have to handle APC, setup. It's not just a function call, it's some, you go through some manager where you say, look, where is my TCP stack? Here's your endpoint. It's not super hard, but like 27 million lines of code will not go away. So if you really want to run, support the same hardware, you will end up with the same 27 million lines of code. But natural observation is that those guys are isolated, and the only shared part is this tiny microkernel, which can fit easily in 10,000 lines of code. And for that, we have a practical technology which today can verify. So then you're kind of building from the ground up. You say all the shared subsystems can be verified. Maybe you will verify PCI next, because okay, if PCI goes away, then the whole system goes away. Then you go, okay, I will start verifying device drivers. Maybe, but maybe it's not like 27 million lines of code, but if you're deploying in some mission critical system, you can just verify specific subsystems which you care about. And if you design the interface of a microkernel carefully, then what you can do is you can, and this is what's worth doing, and it totally should be done. And I'm pretty sure that everyone who's building from scratch today does it. So like I've heard anecdotal stories that those companies, automotive companies like NIO and Draco is a supercar. They essentially build those microkernel architecture. Actually, NIO supposedly runs a CL4, right? So they actually run a verified microkernel in their cars. If I'm not Drago, what's the word? What's the name of the car? Like a supercar, American supercar runs partitioning microkernels, that's hypervisor. But essentially what happens is that they build the systems which look like this, which use this argument of strict partitioning, saying that, okay, look guys, the microkernel is shared, maybe verified like a CL4. But then you say, look, my mission critical parts are running on one side of this partitioning boundary, and my non-critical stuff maybe running a Linux inside a virtual machine. And maybe it's like full Android or something, which shows you like your infotainment system on the screen, right? Where you play your music and enjoy whatever other things from a modern car. But this partitioning boundary is so strong, enforced by the microkernel, that your mission critical parts like, I don't know, steering, whatnot, sensors, microcontrollers, run those processes, and you either rigorously test those or even verify, right? And if you have a bug here, then here micro reboot does work because it's so independent from the rest of it. Maybe you have some kind of like a manager which sets it up, but essentially this thing essentially can reboot. I mean, I don't know what happens when you reboot your car, but maybe it stops for a little bit. But maybe this keeps driving. You just lose your navigation system, right? And then it reboots. Not transactions. I have consistency. But this is like, you get the argument. And the beauty, the real argument, why it's possible in those systems, because this microkernel is engineered towards providing this strict partitioning. And it's almost impossible to introduce inside Linux, because it's like C groups and everything, but still there is a lot of shared state and not clear how to partition it. And here you can even say that, look, we are so clever that these two things are running on two physical CPUs and cannot even like, you know, play those scheduling games with each other, because any process from this part of the system, which is visible here as a microkernel thread, can only be scheduled on this CPU and will not be able, the system will never migrate it to this CPU. And so like you can design it carefully, right?
What would the schedulers sit in this design?
Well, you will probably have, like, similar to what we were discussing last time. There will be a per core schedulers, which essentially run their own per core scheduling queues. And occasionally there will be an act of rebalancing, meaning that, like, just for the sake of it, let's make another drawing for another CPU. And you say, look, suddenly this scheduling queue is completely empty, and they communicate between each other, and it's like essentially rebalance the execution load, moving these two threads to this CPU, and this is allowed, but moving anything from here to here is not allowed by.
Even that level sounds good. The next second on top of this here.
Yeah, okay, so how does it work? Who can tell me? A CL4 for our microkernel sees it, for example, as thread 4, 3, and 5, and just schedules them. But your Linux might have like hundreds of different threads and stuff. So how does it work? Oh, that's one way. Yeah, virtualization is also good. Yeah. If you wanna think of it in terms of virtualization, for sure, let's think of it in terms of virtualization. But we can, and maybe it's a useful abstraction. But how to build this? And remember my use case where I was showing you a user level context switch, where we just essentially what was happening is that in our code we created two functions. I mean, I forgot, maybe I was just literally running one function, but imagine you have two functions for bar, or like, I don't know, process 1 and process 2, and essentially they were muting inside, right? And this ute code was context switching on one Unix, on one POSIX thread, right? So essentially here, when I was muting, I'm just in some internal data structure, I say the state of my thread, logical thread, E2, into some data structure, restore the state of the thread, E1, and run it on top of a real thread, which is visible, which the kernel manages and schedules, right? So it's kind of like a scheduler on top of a scheduler, right? So we just assume that this thread, which microkernel, or the kernel in my case, will eventually run according to some fairness policies. But internally, I'll kind of like run two threads. You can think of it as two async primitives in your language. But if you feel like, you can create a POSIX-like interface. I think it's called green threads or something. Like essentially user level threads, which context switch execution of two functions. Typical interface will be create thread plus a void function, which takes a void pointer as an argument inside the POSIX interface, and then have a signal which receives the timer interrupt or something like this. And periodically, if you don't have cooperative yield, then you context switch forcibly between those. Right. So the same works, like the same works here, except that, like you say, how does virtualization works? So this kernel sees some abstraction of a CPU and uses some kind of a system call to a microkernel saying, okay, look, we don't even have to do a system call, right? We just need to receive some kind of a timer events and then context switch those contexts of execution which are visible to you on top of it, right? And this is how virtualization works, honestly. Does it make sense? Okay, so, but essentially the goal here is that if we start from ground up building this partitioning microkernel in such a way that this boundary is strictly enforced, and it's, if I ask you a question, so what do I mean by this when I say strictly enforced? What kind of properties this microkernel should have to make sure that this boundary as strong as we can imagine?
It means everything and pretty much on the right side of that partition can never affect anything on the left side of the partition, memory wise or process wise, execution wise.
correct, but what if this guy does something like a malloc here? You know, like you're creating a new thread of execution and both of them say, look, I want to allocate a new thread. So how do you partition memory, for example, just as a use case? How? Well, because it's a microkernel, like we still share, like we still have one physical memory. They remember those linked lists which you just built, right? So
Just right now, it doesn't seem that complicated to me now to like reserve. Allocate. We have like one allocator that services calls. Services calls.
Yeah.
You know, less.
yeah, that's one possible approach. Remember, our allocator was more like a linked list, right? And we can say, look, when we start this, maybe we're going to introduce some notion of this, I mean, let's call it a container. And when we create a new container, maybe we say, look, this container has a reservation of 128 megabytes or something. And we immediately, when we create the container, we take 128 megabytes of the available memory from the linked list, put it on some other special linked list and say, look, all the memory will be serviced from this reservation, right? So that's one way to do it. And there are different ways to do it. You can also say that you can make this reservation in a more virtual manner. You can say, look, I track, like imagine you have some kind of a root container which had all the memory of the system. And then this root container says, okay, look, I'm creating another container and I'm donating 128 megabytes of my memory to this other container. So it can just say, look, essentially reservation of this guy drops by 128, just as a number, and this guy's grows by 128. And essentially, at this point, you know that this guy, or like if this root container creates a second partition, like let's call mission critical or entertainment, and each gets R28, then total memory was reduced by 156. At some point, if this guy tries to create a third container and give 128 to this one, if it doesn't have sufficient memory, creation just fails, right? Because you say, look, you don't have. We know that it's all virtual, this memory is not used, but we know that someone reserved it, right? And those guys, every time they do malloc, they go to a global list, but they check, the allocator checks against their reservation first. So it's more like a virtual reservation of future use of memory. So you don't have to physically split the lists. On the other hand, you might still want to do it if you say, look, guys, I know that my list is under a spin lock. And for whatever reason, like in our homework, imagine it's just one global spin lock. And maybe it's possible to trigger some kind of a memory operation. Maybe this guy can allocate a ton of memory upfront and then try to deallocate it at once. This deallocation acquires the lock on the global list. And then those guys who try to execute something on this allocator are just sitting waiting on this lock and starving in terms of like time, right? So they experience higher delay and maybe it can result in some critical crash or something, right? So if you want to deal with those kinds of attacks, then maybe you have to split the lists upfront physically and make sure that you're not even conflicting on spin locks, right? Make sense? Although it seems intuitively that this might work in many cases, but maybe, I mean, it depends on how far you want to go down this road. Oh yeah.
Isn't the other thing we're splitting physical CPUs, like guarantee that the critical system has at least one CPU that it can always do work with?
That's a good question as well. So, and that's coming back to your observation. I asked, okay, how to split the system? You said memory, execution. I illustrated memory, and I wanted to get to this, like two conceptual design points where you make reservation kind of virtually or more physically to avoid conflicts on spin locks. But the other completely different story is how do you reserve CPUs? And what does it really mean? So it gets a little tricky, right? Because if you physically have like two physical CPUs, you might set a specific flag saying that those processes and every one all other children of those processes inherit this flag. Or everyone who runs inside the container has a specific mask of CPUs on which they were supposed, they can be scheduled, right? And maybe we set the mask in such a manner that this mission critical container and infotainment do not overlap on a single CPU, for example. And at some point you say, look, but what about if this one wants to set up yet another container, because for whatever reason, this infotainment system also doesn't trust whatever, I don't know, multimedia players or something, which consume all the available CPU or something. But at this point, there is no other physical CPU, so you cannot really split them, right, at this point, like physically partition actual physical CPU. So you have to play with the scheduler, right? And again, okay, so how can we approach this? So how can we say, look, or just for the sake of example, can we build the same partitioning with only a single physical CPU? So how to do this? What will we do in this case?
Maybe you modify the scheduler such that half of your time slices are guaranteed to be given to the critical system. So this would be, and then you further subdivide each half based on whatever scheduling.
Right. So, and I agree with you. So, and that's the answer I would give you anyway. So if you can't really partition spatially, meaning that you have two physical CPUs and just spatially partition them, you have to partition temporarily. And you probably have to design a very simple scheduler, which maybe just says, okay, I'm no weights, nothing. Just I choose a slice, 1 millisecond, and 1 millisecond goes to one partition, another millisecond goes to another partition. It's only partially solves the problem, because what if you say, look, but I have to run every 0.10 milliseconds, then this thing starves everyone. So then you go back to the domain of scheduling where you say, look, I don't know what to do, like fairness is fairness, but I really have to run this thing, otherwise I'm screwed, right? And there is no real good answer. This is in the domain of real-time scheduling, but yeah, probably you will choke those dice into 10 chunks and say, look, yeah, I'll stick my like 1/10 of a millisecond execution in between your intervals, and if you can't play the video or something, forget about it, right? But there is really no great solution, right? But that's where you are. You will try to play with a scheduler. And the domain of real-time scheduling is a really tough domain. So at some point, there was a ton of literature. I used to read it, then I quit. But really, it's almost like this shortest deadline first, but really you try to reason about deadlines of multiple or like conflicting activities and say, look, like can I still fit them in? And then probably can, or cannot in some cases. Right? But essentially, yes, there's temporal partitioning, and it's hard, but on top of it, it just doesn't solve all of your problems because you have shared caches, shared memory subsystem, right? And so you say, look, I usually run every 1/10 of a millisecond for like some small amount of time, but if the second thing, which context switch, just evicts all my data from caches, it just slows me down by so much, and then you lose this predictability. And for that, we have cache coloring, but it's only last level cache. You can kind of partition the cache, saying, okay, you can only use those cache lines and evict whatever you want, but you can only evict from your own partition. But I don't think cache coloring at the moment works above L3. So if you really have one CPU, then caches L2 and L1 still will be affected, right? So L3 can be colored and partitioned. But also, like, there is a ton of stuff, like, so yeah, so getting this boundary absolutely strong is a hard challenge, honestly. Just it goes into the hardware, so like even into the network interface, which says, look, now you have to either somehow in a fair manner multiplex this device queue between two activities, such a manner that they cannot affect each other, which also looks unrealistic. Or you ask hardware manufacturer to exploit two different queues and partition those, but still somewhere down below here in firmware, they will be multiplexed into one real, whatever, physical decoder and stuff. So it's hard, challenging. So you had a question.
When you're talking about caches and having that shared, I mean, would it be enough to do some sort of a worst case performance analysis and like maybe that could be sufficient?
Correct. That's a good idea. And so another reason for using the microkernel or kernel in those scenarios is that microkernel actually, I think, is as of now the only implementation on which this worst case execution time analysis was actually was rigorously and mathematically proven to have specific bounds. Because if you take Linux and you start some kind of a symbolic execution or something, trying to figure out the worst case execution time, it just doesn't converge in many cases. Just like the code base just doesn't have this bound. Here, I think a CL4, because they have approved that all the loops terminate, and then you can build the static analysis and say, look, I know that the worst case, a CL4 is funky because even imagine you have a very a large address space, which has a lot of mappings in the page table, just because it's giant. Maybe it was running a hash table. And you suddenly say deallocate, right? And you say, look, remember in explicit, we just implement the loop and walk entry by entry and deallocate, right? But typically you do have to acquire a log on a page table, just because that's like sooner or later you will end up acquiring the log. A CL4 is actually under one big log, so the whole microkernel is logged under one big log. But this operation doesn't have a worst case bound, right? Because if the address space is giant, your bound grows. And so what the CL4 does, it splits it into batches. It says, okay, I will execute 100 of those, and on that one, and then I exit and we'll do something else. And you have to continue. So you cannot deallocate the whole address space at once, but in chunks. And it's kind of a clever idea, kind of say, and then you have a worst case execution time of this chunk. And then this part, which is mission critical, can be guaranteed a specific, time slice. So, yeah. But so time is still probably a research question. So it's not fully solved, as well as all the side channels, which essentially data is leaking through all these caches, different queues which connect those caches, and the memory subsystem, and whatnot. You can there are probably hundreds of papers at this point on different kinds of time channel attacks. So on this again, partitioning is hard, but still probably that's the most promising direction. Okay, so we got to, this is kind of the high level. So if someone hires you and says, look, build me a system for my autonomous vehicle or an insulin pump, which is also attackable and very dangerous, right? So please go with this design and say, look, guys, this is the best we can do. I used to say that this can be written in Rust, but then one of you says, okay, guys, it's all unsafe Rust. So what kind of advantage it gets us? Doesn't really give much advantage, because this small piece is so densely unsafe that really it has to be written it has to be written in a tool which allows you to formally verify correctness of this microkernel. Right? Makes sense?
What are the unique constraints of an insulin pump? I wouldn't expect it's also running Linux. So what's it doing?
The constraints is that it can harm or unfortunately even kill the person if it's attacked, right? So you can physically, it runs a Bluetooth stack most of the time, because it's controlled with, not always controlled, but at least has some communication with the phone. And then if you break into the pump, and it was demonstrated in the research experiments, then you can administer a lethal dosage of whatever insulin, right? So, and it doesn't run Linux, I would assume, in most cases, but it runs some kind of embedded systems, maybe even microkernels, and still without any verification guarantees. So it depends on what concrete system you're looking at, but maybe most likely it's just the logic of this, whatever you compute the dosage per unit of time, you can attack it and just compute something completely different. But maybe you can also attack parts of the system and just do whatever, like denial of service, and it just never runs again, something like that. So insulin pump I used historically in some of my proposals to scare people. Don't think it's ethically, very pleasant, honestly, because you're playing on this edge. It just gets too close to be scared. Like, but you do get scared. Right? But at least like anything, like you build a smart lock, just build it this way probably with some kind of microkernel system. But okay, so that's fine. So hopefully that's essentially like take away from this class of the systems should be built this way ideally. And if you read, like, if you say, look, what about backward compatibility? You always say, look, this thing works as a hypervisor and it runs Linux and top, but in some kind of a partition. And so whatever happens there, it never escapes, right? Besides maybe like some, whatever, cache pollution or something along those lines. But one thing which I wanted to make sure we all understand, which we still didn't talk about, which kind of is important for constructing this system, is access control. And this is what I was asking. Okay, guess what it is? Okay, imagine we boot it, just to make it concrete. And the end goal is always this system. And let's say the end goal, again, this partition, which I can bring in out is, people call this microkernels, partitioning microkernels, meaning that, or partitioning hypervisors, meaning that you can have strong guarantees that one side of the partition cannot interfere with the other. But in order to achieve this property, you somehow need some kind of a mechanism to say even, look, let's imagine there's like, just for the sake of it, 2 devices in this system, or maybe even 2 cores. You need some kind of mechanism to say that this process 1 is allowed to talk to this device, but not to the second. And maybe process 2, and maybe it's like a network interface driver, and this one is NVMe storage, and talk to this one. And maybe you can even say that, look, like you say, this can be scheduled on this CPU, but this can be scheduled only on this one. And just in order for us to build this partition, right? So what kind of mechanism we need to make sure that we can express those constraints in this system? Can you think of something? What can, or like other examples, like if this is physical memory, we say that this guy owns a chunk of this physical memory, and the other guy owns another chunk. And then they cannot, like, let's imagine they can't even, like, it's a very concrete reservation. You say, like, that much physical memory you can own, or maybe even the specific region of physical memory. Maybe it's on a NUMA machine, it's local to you, but cannot affect anyone else by somehow affecting their NUMA partitions or anything like that. So how can we express this in this tiny microkernel? What would be a useful mechanism?
Like we can just track ownership at the application level. Like even this reservation is going through some interface.
Okay, so but how do, okay, what you're saying is that like you say, imagine there will be some kind of a connect system call, and you pass a number, let's say 1, and it allows you, it gives you a bar back, and you can talk to this device. And if you pass 2, you say denial, because 2 is far for this guy, right? But how do we bake this policy that this process 1 can access this device, but process 2 can access only this device? And what if these 2 guys don't even exist because originally only one process booted. And maybe the one that this process can access everything, but then kind of give away those rights to access other devices, to other processes as they get created.
So essentially, like, how are the drivers? Like, how do we create a secure channel for the driver?
Or express the fact that you can say secure channel, but express the fact that this specific process P1 can access some resource of the system, like maybe a CPU, and can be scheduled to this queue, or can access a specific device and can, for example, add one of its own pages to an IOMMU of this device, meaning that device can write into this page, right? Or even, yeah.
So that, I mean, the driver and the device will have to do some sort of patching to make sure that they belong to the same. Like, you wouldn't want the NVMe driver.
Yeah.
So that, like, maybe we can bake in like a signature itself that the driver knows about. And then it's just a matter of the processes themselves.
Okay, like, well, we can go this brainstorming pause, but let me like just to make sure that we'll finish today. How do we do it in the physical world? What's the, imagine those are cars. And you are allowed to drive a specific car with keys, right? At airport like this. Yeah, we do that with keys, right? Yeah. So essentially, someone hands us a key, and then we can use this resource later on, right? And there are different ways of how to distribute keys, meaning that you can, but as I was saying, it's not ideal, but roughly speaking, you can give this process one kind of keys to all resources in the system, right? And then this process can selectively delegate those keys, meaning that like when we implement our endpoint mechanism, we can implement logic for passing the key across, right? And then if this key corresponds to a network interface, then this key now lives in this, like somehow lives in this process. And when you implement a connect system, when you invoke a connect system call, you pass the key as an argument. And the microkernel says, okay, wow, I see a key and hope it's connected. It's associated with this device. So sure, I will allow you to map a bar region back. But if you don't have a key, then you can't really express the fact that you're trying to access another device. You might not even be aware of the fact that this other device exists because you don't have even a way to name it because you don't have a key. There is no like magical name to say, show me an NVMe device. If you don't have a key, you don't have it, right? And this idea of keys is called capability access control. So capabilities are kind of like system level implementation of a key, right? And we did see it in x86. In x86, the file descriptor table was implementing keys. You use the keys as numbers. You say, look, I want to use key number 0. And here, this was associated with a specific file in the system, right? In x86, although you can use like a open system call and use a name to say, look, like search the file system and please give me a key which leads to any file in the file system, roughly speaking. You can use it as key number 3, 4. But you might say, look, if I don't have this open system call, then you essentially need to have a key in order to even access a file.
So on Sherry, capabilities are the validity is tracked and you can really modify them with hardware instructions.
Mm-hmm.
For systems without that hardware support, how do you keep these capabilities secure?
Yeah. Okay. So good question. So on Cherry, Cherry is a slightly different like idea or slightly different use case of the same keyword capability, which in some, like, they do overlap, but it's like two different universes. The question, how to build the idea of this key? Like really, it's not like a coincidence that I was using this file descriptor table as an example. Imagine if you have resources in a system, or even like a chunk of physical memory, right? The microkernel itself says, look, guys, I know that you have very primitive logic to maybe enumerate PCI resources, or you can even delegate it to a boot manager to do it for you. And then for each of those devices, you associate like a real data structure, right? Like, I don't know, device 1, device 2, and some data structure which represents the region of memory, right? And imagine now you say, look, guys, I get this idea. So how is it supposed to work? So you build some kind of an indirection table where user processes can only use some abstract key names. Let's use numbers, for example, for now. And if there is something, a pointer, which points to a specific object in the kernel, and you have to keep track of a type, obviously, then you say, look, I know that this is an object of a type device, and it means that you can implement one generic system call invoke. How do we spell invoke? K? Just K? No C. And then if you pass this number, and I will use this symbol, which is a number, then you can say, look, I don't know, open. You can specify an operation. It's almost like you having like, I don't know, an object, and it's a method of an object, right? And the way for you to resolve the object O is through this generic invoke system call. And this guy goes into your table, which is somehow attached to your context of execution. Maybe it's a thread, for example. It's logical to associate this table with the thread of execution and say, look, on object 1 in this data structure, which it's a good name. You can call it as capability space or a C space. This is how ICL4 calls it. Look up the object, which I know as 1, and if the type, I mean, maybe you can provide the type here as well, just to make sure that there is no type mismatch, because maybe multiple will have open. Implement this operation open, and something happens in the kernel. And maybe a result of this open is that the microkernel says, okay, I know that this has a bar region associated with this device, and the result of open is that it does get mapped in your address space as virtual address, right? And this is how it works. And if you say, but what if I don't have it, or it points to a different type, then you receive an error, right? So, and this way you can kind of like have a unified interface to invoke any resource. And again, think of it, and the easiest way to think of those systems is in terms of object programming languages, I think. But it just underneath everything is like across a system call interface, right? And you just say, well, do something on number 1, which I know as, I believe it's a device, and I keep track of what capabilities I have. And then you can say, if we have a send system call, you can send a capability across, you send 1. Well, if you want to be very concrete, we say, look, this will be a capability to a rendezvous point, right? Because you need to name a rendezvous point or an endpoint, right? So your 0 will be pointing to an object in the kernel, which implements an endpoint, and you pass capability number 1 into this endpoint, which means that whatever this capability points to, device driver, goes from sender to a receiver, right? If you do a receive, and maybe here you also have a capability, and you know it has capability number 33, and you say, please receive into capability. Either you unspecify the number, or you say depending on how you want to structure your microphone, you say receive it in slot 4. And then if you have this capabilities space implemented as an array, for example, and 33 points to the same rendezvous point, then your new capability number 4 will be pointing to this device. And now this guy can do open of 4 and whatever, provide some argument and get back to bar region map, right? Make sense?
So this sounds just like file descriptors. Is
Very
there a
much.
nuance for how they're different?
Right. Well, that's a very sound observation. So first of all, it's very, very much like file descriptors. Let me ask you a question. But first of all, we understand how it works. It allows us, it's kind of similar to how we played with file descriptors when one process creates another process, then you can pass some of your file descriptors to a child, right? But in x86, you cannot pass a file descriptor across. In Unix, you can, right? So you can pass whatever, use Unix domain socket or whatever, allows you to send file descriptor. But here, send receive allows you to send those capabilities across. So what do you think has to be different in this system? Like, what is this nuance? Why it's, can we just build it as these file descriptors and be happy? Creating what?
Creating like a capability.
Out of nothing.
Yeah.
Well, if you carefully design your system calls, they will never return anything what you don't own already, right? But for example, you can say, well, how I create a new endpoint, and you can imagine like create endpoint system call out of nothing. It creates an endpoint, a capability pointing to a new endpoint. And that's fine because it's within the process, right? It didn't leave yet. However, now this process can send this capability to another process, but only to the processes to which it already connected. There is no way to make up a connection. If we were not connected, we will never get connected unless we are introduced, meaning that someone else sends via capability to your endpoint by introduction, or through creation, meaning that probably it makes sense that the parent has an endpoint of a child to at least like introduce the child to everyone else, right? So it's kind of when normally when you create a new process, and you might like specify which ELF image you want to map there, you get a capability back which points to the endpoint of this process. And so the parent is connected to a child, and that's similar to Unix, where parents are connected to children. But then if you have endpoints to the rest of the system, you can introduce the child to everyone else, right? And it makes sense because this allows you to kind of control, if you have those islands, you will never cross the introduction boundary between islands. If there is no endpoint connecting the islands, in theory, there is no way for them, unless there's a bug in a kernel, there is no legal way to pass a capability across and introduce. And the bootloader, which created these two islands, may drop those capabilities to endpoints, to original endpoints, and just there is simply no connection in the capability graph between these two, right? And that works, right? So it seems to work. And this is how it works. Okay, cool. So, but back to the question, is it sufficient to use this file descriptor? In fact, I think it is in many ways sufficient because we have a way to send capabilities across processes and receive them, right? We have a logic of system calls, which essentially, there is simply no way to reach out a device unless you already have a capability to this device. And maybe you just have to play a certain boot protocol where a process which we can call master 0, or I don't know, bootloader 0 has capabilities to everything in a system, and then it allows you to push the logic of system configuration outside of a microkernel and solve it at the level of bootloader 0. So it essentially splits the worlds whichever way you like, right? So, but okay, so that works, but there is a couple of interesting properties which we want to implement. So one property is that if in this system everything is a capability, you can maybe reach easily millions of capabilities. Because if you say, look, I will be splitting my memory in chunks, making sure that each chunk is identified by a different capability, right? And this is what the CL4 does. Then probably array is not the best data structure because you will run out of either it's too big or too sparse or whatnot. So this gets replaced with a tree-like data structure. And you can use like a radix tree or some other tree. I think ACL4 uses something what is called, I think it's called a guarded radix tree, meaning that it's a radix tree which changes the radix as it grows, and meaning that initially it can be roughly an array, but then it starts pointing to additional levels, and I don't remember how it's built, but kind of like dynamically changing the depths of the tree, right? And it allows you to conveniently balance like space of this data structure with the possible sparsity of this tree, because maybe you will end up with a ton of capabilities, especially like this bootloader 0 has a ton of capabilities, but maybe not. But as you split memory, you can end up having a capability to each individual page, and that's a ton of capabilities, right? So that's one, but it's kind of logistical thing, and you don't have like, okay, sure, yeah, that's optimization. That's fine, but there is one other important property, yeah, which the system, we usually want the system to implement. Let's imagine. Let's imagine you had this scenario in which a bootloader 0 had a capability to a network interface, created another process, plus this capability inside. This guy created another process, plus this capability inside. And then suddenly, maybe this guy crashed or something. Or in general, maybe it just starts falling, and this guy, bootloader 0, says, I want to kill all of it and create micro reboot everything from scratch. And at this point, you have a dilemma. You're saying, look, but what if this guy still can talk to the device? It's probably not okay to allow the boss talking to this device, right? And maybe you actually want to reclaim all the memory which you gave to this first island back in order to create the second island, because maybe they just don't fit because it takes too much memory altogether. And in a physical world, it's kind of like, it's a property which is called revocation, meaning that at some point you say, like, I gave you the key, you can drive my car, but at some point I want a key back. In physical world, it's hard to implement, because if you pass the key to your friend and your friend ran away, I mean, I don't know what you're gonna do, but we have like policy. You go to a dealership, says, okay, here's the card, like there's no key, so they make you a new key. But how can you solve this problem here? And like essentially the system which I explained up until now allows you to, in a fine-grained manner, delegate rights. So this is how it's called, fine-grained delegation. It's not like you say, look, if you have a ton of capabilities, you can like create a new process and give just one, right? So it's fine granularity. But we need a second property, revocation. So how can we build this second one?
What if you make it such that when you want to revoke a capability, you find it in the capability table for the given process, and you mark it as unusable, and then so then it's kind of like a memory allocator. At that point, the number could be reused for something else. So then the number, if you use it kind of like a use after free later, now it's going to refer to something else, but not the thing.
No, in a way, I agree with you. You say, look, let's find this capability and invalidate it. And next time someone does invoke on it, it just is denied. Or if it was a memory page, the part of revocation will be that the page is unmapped, And if you have a page fault, and okay, that's kind of a cute little exercise how to build pagers in this system, because sometimes it's self-paging, but sometimes you say, look, some other process can be a pager for me, right? But let's put it aside. But let's say when map the page.
This case.
You don't know where?
Unless the colleague tells you that I'm done.
Right. So the question is like, do you support like a forcible revocation, meaning that no matter what you're doing, I'll just take the resource away. In Unix, it's all implemented in a one single primitive, which is kill. You say, look, like if I'm not happy with your usage of resources, I'll just terminate the process. And hopefully all the resources, the kernel will just garbage collect everything what you were using. Like if it was a bar region, it will probably get back to the kernel. But here we say, look, can we, in this system also, like Talia, I wanted to follow up on what you were saying. You say, imagine I'm a parent and I come into a nightclub and say, come up to Monvik and say, Monvik, give me your keys. Monvik says, like, what keys? Like my daughter gave you the key from my car. And he says, no, she did not. And the thing is that, I mean, the bottom line here is that how do you express the right that you have a right to revoke something, to take something back? Because in a Unix, the kernel can revoke anything or a root can revoke anything. But here it's everything fine-grained. I have to produce an evidence that Monvik has my key, although there was a chain of people in between two of us, and I somehow just know that he might have my key. And then every month you revoke, you have a grant. Yeah, that's it. That's a good example. So that's the way to revoke. But imagine we want to revoke now instantly. How can we build this, express this property? Okay, so yeah, so okay, I have like 5 minutes or something. Quickly explain. So there are multiple ways to do it. So one classical way to, in a programming languages, like for example, you say there is an object which sits here, and there is, let's say, Alice, and like I want to give a capability or like a pointer to the interface of this object to Alice. If you pass it to Alice in programming languages, Alice can use this pointer forever. A classical solution is proxy. I create a proxy to the object, and I pass Alice a capability to a proxy. And the moment I'm not happy with Alice, since I have a pointer to the proxy, I say like stop. And no matter what Alice tries to invoke, normally proxy would forward all the invocations to my object, but the moment I say stop, invocations are not forward, right? So it's a proxy pattern of revocation. It's not ideal here because proxying introduces additional, like layers of interaction, stuff like that. But there is a domain of object capability languages. I don't know if you guys know, but this is the idea from this language.
Do you have a single proxy for all the objects in Gladys?
Hold on. Let me just quickly explain the solution here. So here, what a CL4 microkernel does, and it's the same approach. They maintain a second data structure, which is called capability derivation tree. And essentially, if I have a capability to a resource, first of all, capabilities always follow a specific set of rules. One of them is monotonicity, meaning that if you have a capability to a region of memory, you allow to create a new capability to this region of memory, and this operation is called minting. But this capability should be either same power or slightly smaller, right? So it cannot exceed, right, the size of this memory. So it's same to make it short. But this capability derivation tree essentially says, okay, guys, I keep track of connection between derived capabilities. And every time you do, for example, a send operation, I record the fact that receiver received this capability from this original capability, right? So you did the receive, you have a capability that points to this resource, maybe a region of memory, maybe a device. This receiver uses a send operation and sends yet another capability to someone else. And this someone else, like this is P1, this is P2, also has a capability to this resource. But the capability derivation tree tracks the fact that this capability was originated from this one, right? And it's really like a tree. You just like, because here you can like create multiple versions of this capability, send them to different, like, right? Because why not? Maybe flexible enough to support this logic, right? And okay, if we have this capability derivation tree, then we can define the operation revoke operation. And revoke recursively traverses the tree and invalidates all minted or derived capabilities starting from the first one. And this is how it's done in the CL4. Instead of doing proxy, nothing is proxied, but every time you either mint or send a capability, you always have the fact in your capability derivation tree. And if I'm at the root of the tree and revoke, then I know that the act of revocation clears the system. And so if we design a system that all the memory is expressed, ownership of memory is expressed in terms of capabilities, I know that if I once, like long time ago, I created a container, I gave it a reservation of physical memory. If I keep track of the fact that I use these specific capabilities, no matter how many containers were created later, and whether this memory was flowing through the system and mapped somewhere else, I can do a revoke and get this memory back. It's a powerful property because it's kind of like if you can force a system, a misbehaving system, to give resources back, right? So if someone was running your network interface, you say revoke. You don't even have to terminate the process. You just revoke the resource and you get the device back, and you have a guarantee that no one in the system can access this device. And you can, from clean start, create a new partition and send this capability inside and start from scratch, right? And this is the elegance of this CL4 interface. They implement this capability derivation tree approach, right? The disadvantage of this approach, which CL4 people will never admit, but probably it's worth like starting in like, rigorous academic discussion, kind of publish a paper, criticize this approach, is that revocation is not much better than terminating something. Because the moment you had a device driver and which had a piece of memory which it got from somewhere, which was using to I don't know, access the ring buffer, and suddenly it gets unmapped, it crashes with a page fault and whatnot, right? And then immediately, it's almost like it's not useful anymore. Like, I don't see a way to recover from this situation. Or you revoke the access to the network interface. At this point, you can very well terminate the process, and it will be intangible results. Probably it's almost the same, but that's, I don't know the answer. So in our wonderful system, we said, okay, forget about it, just kill. And essentially we just terminate, we just keep track of chain of who created whom, and you can terminate if you own the chain. And that's good enough, but sometimes you cannot revoke all the memory, because if it leaked outside of who you created, then you screw it. But that's the idea. Okay, 0 minutes left. So any questions about capabilities? So it's also a very powerful construction primitive. So for microkernels, and again, it's powerful towards this idea that you can, if you express even ownership of memory in terms of capabilities, you can split the memory. And imagine you can encode specific mint properties, kind of like that. If you want a capability to a subset of this memory, then you can split it in half, and there will be no capability which overlaps like this. So it expresses, simplifies reasoning about what's good. Okay, good job, guys. So I will see you next semester. I will assign homework, which you promised to attempt, but you don't have to. And hopefully, hopefully someone will work on something. Okay, done. Thank you for being in this class. Well, I'll teach it again, but better next time. Thank you.